Assalamu alaikum everyone. Welcome to data mining lecture number 25. So today we will continue with our discussion on temporal data mining. We had started talking about temporal data mining in the last lecture. We had introduced the data type, which is two data types actually. We talked about time series data and sequence data. And then we also started talking about some pre-processing steps that are often required for analyzing time series data. So today we will continue with that discussion, talking about some other pre-processing steps, and then we'll move on to forecasting, which is a major task that is typically done for time series data. And I think that's pretty much for today. In the following lecture, we'll talk about motifs and outlier and cluster analysis for time series data. So we do have a quiz at the end of class today. This would be your last quiz for the semester. So we would be dropping two quizzes as we had agreed upon earlier on. The two lowest scoring quizzes of yours would be dropped before finalizing the final grading for the quizzes. So that is basically the agenda for today. Are there any questions? All right, so let's continue from where we left off last time. So we distinguish between time series and sequence data. So what was the difference between the two? So time series data was usually continuous valued. So in general, temporal data attributes can be divided into two categories. We have contextual, and then we have behavioral attributes. So contextual attributes are the reference points or reference information for the behavioral attributes. And when the behavioral attributes are continuous, then we say that it is time series. When the behavioral attributes are sequence, then when the behavioral attributes are discrete, then usually we say it's sequence data. And a special category of sequence data is, of course, strings. Strings are sequence data, which is discrete attributes, but they usually have the notion of order or position, and they don't have any other fine-grained notion of time associated with the values. So just to set up the context again, so usually we have time, T1. Of course, contextual attributes may also include space information, but we are primarily focusing on time right now, Tn. So these are the times at which values are recorded. So what are the values? They are also named correspondingly as x1 to xn. So x, if it is a scalar, then we call this a univariate time series. Scalar and continuous, then we call it a univariate time series. X can also be a vector. So in general, xi, if it is a vector, then usually we'll denote it by a bold, and it could be of multidimensional. It could have various attributes within it. So in this case, then this is multivariate or multidimensional. All right, so when it is scalar, when each x is scalar, then it is univariate or unidimensional. Otherwise, it is multidimensional. And I also mentioned last time, each of these x's could also be some other. It could be it could be data in some other representation as well. So x could be a graph, s could be, let's say, another sequence. For example, it could be an image, it could be a video, could be anything, but mostly we'll be focusing on x as univariate or maybe as a vector. So last time we talked about noise or missing values, and we said that we typically handle that using interpolation. And missing values are usually handled through interpolation. And missing value means that if a value at a particular time point is missing, then you can interpolate it from the values around it. And similarly, if the values are in space, you can also apply geometric interpolation, interpolation in space to estimate the new value. So, and that is simple linear interpolation. You don't really need to have any complicated polynomial or other interpolation. Usually linear would suffice for most applications. So moving on, we wanted to handle noise. So handling noise is done in a number of ways. One is binning, which would lead to a smooth data. So binning is very similar to what we did previously. So we typically bin either equi-width, most likely it's going to be equi-width. So which in our case would translate to equi-time interval window. So for example, you can have a window from T1 to, for example, Tk, some integer k. That's one window. And then you will have, for the next interval, you will of course start from k plus 1 to T k plus 2k plus 1. Okay? So 2k plus 1 and so on. And for each window, you basically can average the values of x's within them. So you can take the average, which is of course mean. You can take the median if you like, which is somewhat better, especially if you have possibilities of outlier in each bin within each bin. And then use those values throughout your time series. So this is the simplest way for smoothing. So usually this would lead to significant loss of information, as you can see for each bin. So let's say if you're monitoring temperature, let's say T1 to T10, and temperature values might vary 25, 25, 26, 30, 26. All of these would be replaced with an average value, whatever that average value is, 26, 26, all values would remain the same in that bin. So the variation in values is reduced significantly. And then of course, there's an issue of border jump. So whenever at the border of two bins, there is going to be a jump. So discontinuity, if you plot it in as a continuous function, there will be a discontinuity at that particular point. So these are some of the pros and cons of this technique. The other technique that we are going to talk about quickly is called moving average. So moving average is more commonly used for time series as opposed to binning. So in moving average, we have a sliding window. So previously we had a fixed window over time. Now we have a sliding window over time. Of course, the window size would be some number of time intervals, but it is slided forward one time step at a time. So just to give an example, let's say again taking the example of temperature 25, 26, 25, 20, 26, 27, and so on. So let's say our window is size 3, meaning that 3 values come into the window. Then, so you move a window of size 3 forward from left to right. So this would be the first window. And you take the average, mean or median, depending on whatever you have chosen, and replace the last value of this window with that. So in other words, this approach would have, you can say, a starting lag. You would not have values for the first 2 points. Or in other words, if you're applying this in real time, you'll have to wait for 3 values to arrive before you can find the moving average for that third value. So what would this be? So 25, 26, 25 average would be so 50, and then 76 divided by 3 would be 25 point something, I think 33, 27, 25.33. So the average would be, you will have basically, you can say a dot, and then 25.33. And then after this, you will have all values. So once you move the, so now you have, this would be the next window, you have slided the window forward. There are 226 and 125 there. So you again take the average. So this would be, so this would be, let me just write it like that, 25. So 26 plus 25 plus 26 divided by 3. So 25.67 and so on. So this is how you do the moving average stuff. So there is a loss of some information at the start based on whatever window size that you have chosen. But after that, the transitions are now much smoother as opposed to in binning. And as I said, this is somewhat more recommended for time series. So the average, the mean can be used. You can use the median also if you like, if you do not like the mean. Increasing the window size in both binning as well as average, moving average would increase the effect of smoothing. Smaller bins would retain the variation. Larger bin sizes would tend to smooth out. So that is a parameter. This window size is a parameter that you can use to control the smoothness of the eventual time series. And then finally, very quickly, let's talk about Expo Smoothing. So this is also common for time series data. So exponential smoothing works in this way. Let's say so far we're only talking about univariate time series. So xi is equal to a parameter alpha into xi plus 1 minus alpha into xi minus 1. So this is the general formula for exponential smoothing. And you see that there's a recursion involved in it. So, and then also we have a parameter alpha. So alpha lies in the range 0 and 1. So it's a scalar. It's a scalar continuous value that can lie between anywhere between 0 and 1. So if, for example, alpha is 1, then the second term in the expression would be 0, and the output xi would be equal to the current output. Okay. So xi minus 1 is usually for the starters, kind of bootstrapping, starting from fresh. It usually set to the current value. So let's take an example maybe. So if you have 25, 26, 25, 26, let's say. So we will set x0 to be 25 for the start. And then we try to estimate y1 is equal to alpha into so x1 is 1 plus 1 minus alpha into x naught. Okay. So this would be the formula. Of course, x naught is 25. And depending on what alpha is, also x1 in this case is also 25. So based on that, you will compute the next value, and then it proceeds in this fashion for future values. So for starting, we set the value of x naught to the first value of x1. So this also approach doesn't have any, you do not miss any value. So you are able to generate a value for each element or each value in the time series. Okay? And there is an element of smoothing based on the previous value. That's why this is called exponential smoothing. And the trade-off of the previous value and the current value that you want to maintain is given by the alpha. So actually alpha is serving as an averaging between the two values. Okay? So if alpha was 0.5, you take the average of both. So this is exponential smoothing, and this also is quite common in practice with moving average. So moving on, let's talk about how we normalize time series data. So normalization. So when we were talking about regular data sets, we discussed various normalization techniques like min-max normalization or z-score normalization and so on. So the same are considered or applied for time series as well. First of all, why would we want to do normalization? So various reasons. For example, let's say you have two time series. One is, let's say, temperature. The other is pressure over the same time interval. Obviously, temperature may be measured in, let's say, millibars, for example, which would be in the range of hundreds, while temperature, if it is measured in centigrade or Celsius, it will be in the range of tens. So there's a huge difference. If you're doing a comparison, let's say computing, for example, the Occlusion distance between the two, there will be a massive Occlusion difference because both of them have different minimum and maximum ranges. So that is the reason why we would like to normalize such time series. And of course, this is all application dependent. You cannot do any of these preprocessings without understanding why you're doing it and what impact it would have on the final evaluation or final task that you're trying to apply. So min-max normalization, we have already discussed this previously. So this is basically based on the minimum and maximum. Of course, this is over the time series. So you have a time series 25, 26, 24, 28, 30. So based on the min and max, min is basically 24, max is equal to 20, 30. And let's say you want to normalize it between 0 and 1. So you will apply a linear scaling between 24 and 30 and 0 and 1. So we have already looked at this formula previously as well. The same formula would apply again. Okay. Similarly, standardization or z-score normalization. which is, as I said, also known as standardization. So this is again a normalization, but this is now based on the mean and the standard deviation of the time series, the set of values that you want to normalize. So after normalization, so after standardization, so new mean would be equal to 0 and standard deviation would be equal to 1. And the values, of course, would lie around 0, negative and positive values. So we had discussed this previously as well. So this is typically one of the more common approaches in time series. Min-max भी apply कर सकते हैं, but z-score normalization is more popular. And then finally, another approach which is called the L2 normalization. You can also use the L1 normalization. So this is basically vector normalization. You consider the time series as a vector and then normalize it with the vector length so that you will get a set of values that would have a magnitude of 1. So let's say आपके पास 25, 26, 27, 25 हैं. You want to normalize this. You basically compute the norm, L2 norm of this vector, which is actually so let's say ये मेरा vector x है, x नहीं देना चाहिए because we are using this x somewhere else. Let's say a. So this is, let's say, your vector. So we are actually dividing each value, let's say 25, divided by the length of the vector. And of course, a is basically computed as SQRT. SQRT. A is now a vector, right? So do a dot product into A. So this is the L2 norm. So this is going to be a scalar value. You divide each value in the vector or in the time series by the scalar value, and then you'll get the normalized output. So this one is also used, and this was not really popular for other types of data sets that we had studied earlier on. So this is more popular for time series. So जब हम time other data set discuss कर रहे थे, ये हमने discuss नहीं किया L2 normalization. But here it is somewhat more popular. Okay, so that was normalization. Now let's talk about similarity. And here I will be a bit brief. Brief in the sense that there is one technique which is actually quite easy, but uski jo nitty-gritty details, I don't want to go into that. So we want to find a similarity measures between, let's say, two time series, and let's say for simplicity those two time series are univariate. And as we said earlier, those two time series, if you're defining a similarity, then you should be aware of the normalizations of those two time series. Otherwise, the similarity would be impacted severely. Okay? So the most common measure is Euclidean distance. And of course, the associated distances, which we call the Minkowski distance. But to apply this, you need to be aware this is applied along the time series. So let's say आपके पास एक time series है 25, 24, 23, 25, and there's another time series 10, 15, 18, and let's say 16. You are considering these two time series as four-dimensional points in space, and then you're applying the Euclidean distance to compute the distance between them. So if this is your view, then you can apply the Occlusion distance or Manhattan distance or any other form of the Minkowski distance. So you have to be careful while deciding how you want to compute the similarity. Of course, now these are dimensions of time. So maybe the first is time t1, second is time t2, third is time t3, and the fourth is time t4. And if you had taken a longer time series, and of course, the number of dimensions would have increased. So in this particular case, of course, so you can think of this as a vector A, and this as a vector B. And then, of course, the Occlusion distance, you all know how to compute them. So the formula that we wrote above for L2 norm, so A transpose B. So this is the Occlusion distance. So let me just quickly show you. So obviously, let's say if you have, let me draw two time series. This is one time series, and there's another time series. So obviously, what you're doing is you're comparing these two values by values at each time point. So the further the 2 points are, the more the distance would be. And let's say if you have a curve like this and another a curve like this, obviously point by point at each time you computing the distance. And let's say if you have two time series which are different shape, but both of them are very close together, now the distance would be very small. But the point that I want to emphasize is the distance is now computed along the time dimension at each point. Or in other words, each of those points are considered as dimensions. Each of those time points are considered dimensions. By the way, this Euclidean distance is used, for example, in clustering or shape comparisons between different time series. Shape clustering of different times. So we'll come to that later on, maybe in one lecture or two lectures. Now, this technique can only be applied, the Euclidean distance and all other measures can only be applied when the two time series are synced, right? So we should have values at the same time point. And let's say if you don't have the value at the same time point, we mentioned interpolation previously. So you can use interpolation to get the value at the same time point. And then secondly, of course, to get meaningful results, and of course, to results that you can interpret, you should be aware of the normalization of each time series. So normalization is very important. Otherwise, the value that you get would be very different for different normalizations or no normalizations. Okay. So by the way, talking about normalization, so let's say you have two time series. एक time series shape दोनों की same है, but of course, because of normalization, one is very high, the other is very low. And if you compute the Euclidean distance between the two, there will be a large Euclidean distance. But let's say if you normalize them, the shape is the same. If you normalize them, then maybe they'll just be over 1 over the 2. And now if you compute the Euclidean distance, it will be very small. Okay. So you need to be aware of this and need to relate this with the actual application that you're trying to address. Okay, the other technique, which is slightly more involved, but I'll discuss the idea and the procedure, and you'll have tools available in libraries that can do it for you quickly, which is popular and applicable to time series. Is called dynamic time warping, or in short, DTW. So what is the issue here? So previously we applied the occlusion distance and we assumed that both series were synced, meaning that they have values at each time step. And of course, both of the series were of the same length. But that may not be the case in practice for many applications. For example, you can have two speakers. Let's say, okay, speaker one reads a passage, and speaker one reads a passage and just takes 10 seconds. While speaker two also reads the same passage, and maybe he's a slow reader and it takes 20 seconds. So the time series for the first speaker, a signal for the first speaker would be over 10 seconds. The signal of the second speaker would be over 20 seconds. So how would you compute the distance or similarity between the two? So they are of varying lengths and they do not sync as in the first case. So this is the scenario for which the D2w approach works. And the idea here is that you warp the time series, either compress it, and what you warp, you don't warp the behavioral attributes, you warp the contextual attribute, the time attribute. You warp the time attribute to expand and contract until you get a good match between the two. And what is the match? You need to have some similarity function, like the Euclidean similarity function. So let's say the time series उसी तरह मेरे पास कोई series A है और कोई series B है. You need to have a similarity function defined. But this A and B could be of varying length, could not be synced as well. So what does this technique does is it iteratively finds contractions or scalings, you can say, of the series and also windows of the two series such that this distance is a minimum. And it does this in recursive fashion until it has done it for the entire series. And that final result will be the final distance or dissimilarity between the two. So as you can imagine, there is an optimization being involved here, because you have to find the best match, and that best match has to be best match in terms of similarity function, minimum similarity. Okay? Minimum dissimilarity or maximum similarity. So you have to check over different time lengths. Pehli series ka, let's say you start with one time period, you check with the other. You expand this with 2, you check with the other. You expand with 3, you check with the other. Expand to 4, check with the other. And similarly for the reverse side. But of course, you do this in a structured way, and you find the best matches with the minimum dissimilarity and repeat until you have done the entire 2 series. So as you can see, there is an optimization involved, and typically the algorithm that is involved is dynamic programming. At the back end, there is some dynamic programming algorithm working to find that distance between the 2 time series that is a minimum. Okay? So this dynamic programming proceeds with sequences of length 1 to whatever length, maximum length that you have for both. Of course, there are 2 sequences. It has to be done for both. So this is sequence 1. The other is sequence. तो नहीं कहना चाहिए, time series कहना चाहिए, but I think you understand. I'm using sequence because the edit distance, which is used for strings, and which is a discrete, is also using dynamic programming. So the second time series 2, of course, here also you expand the window from 1 to m. So after you have run this program, it will tell you pairs of windows of time series 1 and 2 that you can say match or have minimum dissimilarity, and also to give you the overall dissimilarity between the two time series. So in other words, you get an alignment as such कि पहली time series और दूसरी time series कहाँ match हो रही है या minimum आ रहा है, and then of course you get the overall distance or dissimilarity between the two time series. So this is called dynamic time warping, and you will find implementations, many implementations in different libraries, so you can check them out. So this is useful and often required, especially when the two time series that you want to compare do not have synced contextual attributes, and they might be also of different lengths. So you can think of example like, for example, ECG of two people. So maybe the first one was recorded over 10 seconds, the second one was a longer sequence. Maybe the first one pulse rate was higher, the second one pulse rate was slower. So there are variations. So how do you manage that? Through DTW. And similarly, I gave you the example of the previous two speakers, speaker 1, speaker 2. One is speaking faster, the other is speaking slowly. Okay, so this was, of course, if you have strings, string is a discrete temporal data, or it's a sequence data. For strings, the most common similarity measure is the minimum added distance. And this also is dynamic programming. So at the end of the day, you get the alignment of the two strings and a distance between the two strings. Okay. So for those who studied, I think NLP or studying NLP, ये basically हम ये इसकी dynamic programming discuss करते हैं detail में. DTW का भी उसी तरह ही है. The only difference, of course, now would be you have the issue of windows as well. ठीक है. All right. So any questions so far? Okay, the last thing that I'm going to talk about in terms of pre-processing is data reduction. And here again, I'm also going to give you a couple of ideas. The mathematical details I would not be giving. And again, here also, most of these implementations you can find in different libraries. Okay, so data reduction specific to time series, we have techniques from signal processing that are very popular and also reliable or appropriate for time series. So one is, of course, the discrete wavelet transform. The other is discrete Fourier transform. And similar to that, you can also apply the discrete cosine transform. So these techniques can be used for reducing time series data, and they can also be used for other things as well. So I will quickly mention the idea of Dtw and Dft. So DWT, discrete wavelet transform. So the whole idea in all of these techniques is that they represent the time series, which is values at different time points, as a linear combination of some basis functions. So the basis functions, of course, are different for these different techniques. In the wavelet transform, the basis is a wavelet. Wavelet is a small function that is localized in space. So wavelets can be very simple, like a Haar wavelet, which is a step function. So this is localized, so it becomes 0 and only 1 at a particular point. Similarly, but usually for continuous value time series, you will probably use continuous wavelets. So there are many such wavelets. Derbyshire is one of them. So they have different shapes, but I've just to give you say something like this. इस तरह की कोई shape हो सकती है. So at some point, at some interval, it has values, and beyond this interval, the values would tend towards 0. So that's why this is called localized. So it is time localized, and of course it has some frequency, and that frequency can be varied as well. So that's why our DWT analysis is oftentimes called time scale analysis or times frequency analysis. You can localize both the time and also localize the frequency. And your whole time series is now written as a linear combination of such basis functions, which may be at different time positions and they may be at different frequencies. It may be compressed, it may be expanded. Okay? So of course, iski jo math hai, we won't go into the detail. So at the end of the day, you will have something like this, some weights, W0, and some function, which is the basis function, the F0 plus W0, or W1, F1 plus W2, F2 plus, and so on. Okay? So this would be the wavelet transform of my original series. And since wavelets are localized in time and scale, you can analyze the time series more finely, and also you can maybe remove noise. So some of those factors, some of those weights in this expansion might be very small. So you can simply drop those. They might be noise. So this is where the reduction occurs. So instead of now, let's say you have a time series with n values. So you will have n weights once you do the DWT. But then you can drop some of those weights, because those weights that are small do not contribute much to the time series, and they might be just noise. So maybe you can use fewer than n weights. To represent the original time series. So this is the reduction that we are talking about. And as a result, you can also do smoothing or noise reduction. All right. The discrete Fourier transform, the basis functions in Fourier transform are the sine and cosine functions. The sine function is of course periodic, as you know, and it is not localized, it is global. It would have a value over the entire time domain. But of course, its frequency is fixed. While in the case of wavelet, the frequency also would change, and of course, the time domain is limited. Okay? So for time series that have well-defined frequencies over the entire length, then DFT would typically give you better compression. Okay? So for series that have frequencies that different frequencies or one frequency that goes from start to end, DFT would be able to better represent that, and as a result, better be able to compress that data. Okay. Of course, in the expansion here again, the same thing. You have W1 F1 plus W2 F2 plus W3 F3 and so on. These Fs are now sine functions at different frequencies. And for those weights, for weights that are small, you can simply drop those. And as such, you can do reduction and also frequency analysis of the data. So this is the main idea behind these two approaches. And as I said, they are very popular and they are well studied in signal processing. Oftentimes, further processing can be done in the transformed space. Meaning that कि अब आपने let's say कोई आगे classification करनी है या कोई forecasting करनी है, you do not use the original data set, let's say temperature का data था, you use these weights W1, W2, W3. You can also do that. Okay, so it's the transformed space is the space of wavelets or the space of sine and cosine functions. Okay, I think that is about DWT and DFT. Of course, DWT and DFT can also be done for multivariate time series. So far we talked about a signal which you can represent in 1D over time. So for multivariate, there will be some count of shapes, okay, in time. So they can be extended to multivariate as well. All right. So any questions?
सर इन दोनों के दरमियान डिफरेंसेस क्या हैं वो आप हाईलाइट कर दें.
दोनों में से मतलब वो कौन सा बेहतर रहेगा कब?
यस और डिफरेंसेस भी बता दें कि दोनों के तरीकों में क्या डिफरेंस है, मेथड में क्या डिफरेंस है.
मेथड तो हम प्रोबेबली डिस्कस नहीं कर रहे. द ओवरऑल बेसिक अप्रोच तो वही है. यू रिप्रेजेंट एनी लेट्स से फंक्शन y as a linear combination I w I of some basis functions fi. तो दोनों में अप्रोच ये है, बट fi दोनों में डिफरेंट है. एक में वेवलेट्स यूज होता है, एक में साइन और कोसाइन फंक्शंस यूज होते हैं. ठीक है. So once you have done the transformation, you can go ahead and just use the wi's for your future processing. You don't need to transform back to the original space. Okay. So method may, of course, beyond that, I think it will be beyond the scope of this course. So there are approaches, fast Fourier transform की approach है, DWT की approaches हैं. But essentially what is happening is you're trying to fit or learn this basis function, this function and the weights. Okay. So there is an element of learning involved here.
Okay, sir, thank you.
So is that fine or some other question था आपका?
ये भी क्लैरिफाई कर दे कौन सी सिचुएशन में क्या यूज करेंगे.
ठीक है. So usually if you have localized time series, which you can say some time पे वो बिल्कुल dead हो जाता है, फिर बड़ा हो जाता है, कम हो जाता है, so then maybe D2w might give you better representations. But if you have time series has frequency throughout your entire length, then maybe DFT might give you better representations. Of course, there isn't any one way of quantifying upfront which one would be better. If you want to try both, then use both in your final task and see which gives you better results. Final task could be anything. Forecasting हो सकती है, clustering हो सकती है, outlier analysis होती है, and so on. So whichever gives you better performance on that final task, so that would be the one that you would use. Okay, so now we have about 10 minutes. So I will start the introduction to forecasting. So forecasting is a major, you can say, task applicable to time series data. As the name suggests, given values at preceding time steps, we would like to estimate or forecast the value at the next time step. So this is forecasting, and of course it has many applications. So for example, stock prices. So let's say you are tracking, for example, OGDC stock prices. So I don't know what their values are. I'm just giving an example. Rupees में कोई values होंगी इनकी. Let's say 100 था आज, कल 102 था, फिर let's say 103 था, फिर 102 हो गया. And let's say you want to predict the next value. So previous 4 दिनों की आपके पास values हैं. You want to predict the next one or maybe next few. So this task is in general called forecasting. And of course, in this example, this is a univariate forecasting. You have one variable over time, which you are tracking, and then you want to estimate or forecast for the future. So you can have applications in other areas as well. Weather forecasting is another example, very popular example, temperature estimates for the next day. So, and you can also have somewhat sophisticated techniques, although sophisticated applications, which are also forecasting, but we won't talk about that maybe in too detail. Thoda sa idea main bataunga later on. But let's say you have an application, let's say you have video frames of, let's say, a football match. So let's say पिछले 6 frames आपके पास हैं. You're watching a football match, different players, a ball, right? So you have 5 frames, preceding frames, and then you want to decide कि next frame क्या होगा, ball किधर होगा, players किधर होंगे. So that also is forecasting. But now, of course, your frame is not a single value, it's basically a matrix of values. And you are now trying to predict another matrix of value at the next time step. Although अब इस तरह का जो ज़्यादा sophisticated applications are typically solved using neural network, although the technique that we're going to start in bit more detail is the simpler technique, but this is also forecasting. I hope you understand the application. आपके पास different frames हैं, let's say आप football match देख रहे हैं, तो and frames stop at some point, and then you want to predict what would happen next. Maybe you can even think of a security camera catching a particular person moving in an area, and then you somehow you want to predict where next the person would be, and that is also forecasting. Okay. So let's go back to our univariate time series forecasting. If you study or look at the classical techniques for univariate time series, and you typically must have touched upon it in some statistics course, we typically do auto-regression, or we say that it's auto-regressive analysis. So what does auto-regression means? That basically we are looking at the preceding value to predict the next value. But from a more exploratory perspective, there are a couple of issues that you need to be aware of. One is the issue of one is the issue of stationarity, or whether your time series is stationary or not. So what is stationarity or stationary? A time series is stationary if its key statistics do not vary over time. So let's say हम simple time series लेते हैं, like temperature की बात हो रही है 25, 26, 27. If over time, so this is only 3 values, but let's say you have values, let's say 100 points later on. If the average of these 3 values and the mean of these 3 values is the same for any other 3 values at any given position in your time series, then we say that the time series is stationary. So generally, if your time series is known to be stationary, its prediction or forecasting is much, much easier. Or in essence, if it is exactly stationary, you can then say that, let's say iska jo bhi mean hai. So mean is, of course, let's say 26. और इसका कोई standard deviation भी होगा, which I don't know, let's say it's A. ठीक है? So your prediction problem is actually solved. So whatever other time period that I give you, you can tell with very high confidence that the mean would be 26 and the standard deviation would be whatever A. ठीक है? So forecasting आप बड़ी आसानी से आपने कर ली. But this is only applicable to time series that are stationary. And most real-world time series are not stationary, but an idea or an exploratory analysis regarding stationarity would definitely help you in designing better models for your forecasting problem. So there's another notion. One notion is strict stationarity, which, of course, as I said, would never occur in practice or rarely occur in practice. There is another notion which is called weak stationarity, which means that, of course, with some relaxed conditions, usually over longer time intervals or over other, you can say, transformation like differences or logs or exponents, the parameters, the statistics remain relatively the same. So that would be weak stationarity. So let's discuss some of these issues in a slightly bit more detail, and then the models. Actually running out of time also. Okay. So there are generally, as I said, two things. One is the mean. If the mean remains the same, then of course, you can assume that a time series is stationary. The second thing is correlation. If the correlation between a value at any given point in time doesn't change with its preceding value or with any other value that you have decided, then we say that it is stationary with respect to this condition, that correlation is same with the preceding value or with some preceding value with a lag of, let's say, k. Okay. So we will exploit both of these things to kind of first understand our time series and then build models that are better at forecasting. So first of all, mean, obviously, so let's say where is my pen? So for example, usually due to inflation, prices would tend typically to increase. So which means that, of course, the mean is increasing. So it's not stationary with respect to mean. There is variation, but over time, the trend is always increasing. So this is, of course, non-stationary. But if I notice that there's a general trend of increase, then maybe I can create a new time series of differences. So if I create a time series of difference of current value, the next value with the current value, and my trend is something like that, then maybe I will be able to obtain a almost stationary line. So ye horizontal almost ho jayega now. Now the mean is almost horizontal. So that upward trend has been reduced. What did I do? I simply did differencing. So for example, differencing is, let's say आपके पास xi है. So this is basically so xi plus 1 minus xi. So actually इसको फिर xi नहीं मैं कहूँगा कोई और variable कर दूंगा yi. So my new variable is yi. It's actually a difference of the next value and the preceding value. So if I do that, then my line would become more or less horizontal. So this is like weak stationarity. And of course, we also need to explore our data in this way as well. Is there any such relationship in our time series? There's a constant trend upwards, then maybe differencing might be able to make it horizontal or more or less horizontal. So similarly, and of course, differencing can be done periodically as well. Let's say आपके पास कोई periodic data है, time series है यूं करके. So obviously इसका और इसका time जो है difference of course would be very small because this pattern is repeating. Okay? So you need to know the period over a pattern repeats, and then differencing would give you better results. Okay? And then of course periodic हो सकता है, seasonal हो सकता है. You have to find that period. And the third thing that I was talking about, the second thing I was talking about, correlation. So the correlation between any two values. So generally there will be high correlation. If you have any time series, the correlation between two values would be high if the 2 points are close in time. But maybe the correlation will become reducer if the time points are very far away. Okay? But there might be higher correlation if there is some seasonality or periodicity in the data. So these are some of the things that you might want to explore upfront, and then based on that, you might be able to design better models. मेरे ख्याल से I think I'll stop here. We can continue this later time as well. So any questions? So we have a quiz starting in a couple of minutes. So please get prepared for the quiz if you don't have any question right now.
Yes, sir. Today we will start at 6:10.
Okay, starting at 6:10. Okay, that's fine. So are there any questions right now? Okay, I think Nematullah can look at it, but I don't think so. You can quickly change on the fly. Sometimes the duplicates बन जाते हैं, वो issue हो जाता है. तो maybe
Okay, it's 6:05. It's 6:05. So I'm sending. मुझे काफी लोग request कर रहे हैं कि 6.
अच्छा कर लें, बट उसमें देख लें
Yeah.
एक और दूसरे हमने किया था तो वो डुप्लीकेट्स का इशू हो गया था, वो देख लें वो ना
नहीं
हो.
सर, वो अभी मैंने publish नहीं किया तो इस वजह से वो नहीं.
अच्छा ठीक है, ठीक है. So you can always raise questions about the formal contest. शायद नेमतुल्लाह बताएंगे ना, अभी तो नहीं कहा, but ये कि if you have any issue you can discuss.
Yeah. So guys, please turn on your cameras जिन्होंने नहीं किया अभी तक. सर आप ये स्क्रीन शेयर ऑफ कर दें.
हाँ जी, सॉरी,
थैंक यू.
वीडियो